Okay, guys, Team 7, we're doing our technical presentation on altimeters, as you can see, on calipers. Taylor Thomas.
Moses Jones.
I'm Ian McCall.
Ryan Lipinski.
Okay, I'm going to start with a brief overview. Basically, we're going to go in, going to tell you all the types of altimeters. There's lots of kinds, kind of how they're applied, what they're used for. Different types, like I said, the why we're using barometric, and then kind of just our project side. So, where does the altimeter come from, the word? Basically, it was derived in Latin. Altus means height, and metron means measurement, so basically height measurement. Makes sense. Just reading off the slide, but so altimeters are an instrument, which most of you know, that basically tell you the height of something, your elevation compared to sea level. That's how they usually work, basically using many different methods to measure. So, what's the significance of altimeters? How important are they? I just get some shout outs. Does anybody know commonly used devices or anything that uses altimeters?
Everybody.
There you go.
Helicopters.
Helicopters. There you go.
Skydivers.
Skydivers. There you go.
Rockets is a good one.
Those are all good ones. Go to the next slide. So yeah, there you go. So we got planes, of course, and then one I was just on Wednesday. So these have two actually. They use a GPS system, and then they also use analog barometric altimeters, and they're one of the most important devices because you need to know your height, your elevation at all times, because you're usually flying blind most of the time. It's not like they can see out of their windows when they're flying, so it's very important. Then you have stealth fighters. They use a much more sophisticated version. They use LiDAR, which incorporates lasers, and basically they use that. It's basically a really, really accurate radar to fly really, really low to the ground, so they can basically map things out, so they can fly really as close as possible, so it's super accurate. Then we also use it for imaging. If people have Google Earth, and you use that, and you can turn on the 3D map views, well, that's what they use. They use LiDAR, again, they use basically lasers that point straight down to get heights that are very accurate, so that like that you can see the digital mapping of this city. That's a city right there. And then also in basically hiking situations, like these say like climbers, they actually use altimeters to keep from altitude sickness and such, so they can basically judge how much oxygen they need and things like that. So those are basically the common applications.
Next, we are going to talk about the 4 different types of altimeters. The first type is GPS, the Global Positioning System. Today in our world, there are 24 satellites that orbit the whole world communicating with the GPS system. So the GPS can actually work out different location areas of electronic devices, computer systems, and other gadgets that's out in the world. Specifically, GPS trilateration is the relative and absolute location of measured distance points using 4 satellites here today. So you can actually have like a 3D or 2D visual location using this system. The next altimeter type is active remote sensing. It's divided into 2 parts, the radar and the LiDAR. The radar was actually developed during the World War II times, so military aircraft can actually have a distinct measurement of height above ground level during like wars and things like that. Next is LiDAR, and the LiDAR was fairly new compared to the radar. LiDAR was existing and starting from 1960 in the earliest. It stands for light distancing and ranging. Combines a laser focus with radar distancing. Laser adds detailed scanning. What makes LiDAR pretty special is because I have a couple of applications. One major application of LiDAR is meteorology. It's fairly used in meteorology where it can actually communicate and use a topographic map of the moon and it was used in Apollo 15, which is actually found the location of the moon during that. Also, LiDAR actually has a great impact on agriculture, where farmers use this altimeter system to actually detect the amount of fertilizer you can use on a farm and crops. The reason behind that is because the LiDAR system actually outputs digital displays that actually they output digital displays for all the farmland and actually see how much sun is exposed to each crop. So basically, that's how that's functioning. Next is the barometric altimeter, which is the last type. It measures the altitude from by means of measuring the pressure. As you can see on this graph, as atomic pressure increase, you see the altitude decrease. And specifically, barometric altimeters are sometimes input inside GPS systems, so you can actually find more accurate elevations or distance locations inside GPS systems.
So I'm going to talk about some of the disadvantages between the different types of altimeters. For one, I'm going to talk about radar. When we first did our first research about different types of altimeters, we looked at radar, and we realized that we might have to do a little extra licensing with the government. Since we're already working with the Federal Aviation Administration, we didn't really want to add working with the FCC, especially when you see what happens when you transmit on frequencies that are government regulated, $10,000 in fines and/or 1 year imprisonment. So, out of school with our project. A little bit. So, talk about LiDAR now. LiDAR we found might be a little expensive to implement in our project. And also, we're not really interested in the detail that LiDAR can do for the ground. We just want to find the altitude at all times. And also, we thought, where would we put it on our rocket? LiDAR, it doesn't work if you put it straight up in the air because we want to look at the ground. We want the reflection back. And so we thought, where would we put it? We need to put it facing straight down. So we thought it might interfere with our exhaust right here, so out of the scope as well. Now GPS and barometric altimeters are a lot more realistic for our project, but we decided to stay away from GPS because there's a lot of real-time measurement confinements. That's exactly what we need. We need real-time measurements. We need to be able to know exactly what the altitude is at all times so we can actually set off our parachutes. So as far as the real-time measurements, they're really inhibited by the government. They don't want us being able to have too precise measurements in real time because there's the danger, the threats of people manufacturing homemade missiles. So that's understandable. And also, a big thing was the target acceleration of the target. Because with our trilateration, which Moses showed earlier, with the 4 satellites, you're pretty good at locking on the target. But the thing is, when you have a target that's accelerating at several Gs, it really loses its lock. And like you said, that would really inhibit our project being able to launch the parachute when we need it. And for that reason, it's generally less accurate than barometric altimeters. So why we choose barometric? We chose barometric because there's a lot of independence in barometric. You're able to not rely on the ground. You have to rely on satellites either. You can just rely on air pressure, which is pretty constant, and also accuracy. So that for that reason, it's a lot more accurate than GPS, and it's pretty cheap, and it's also pretty easy to implement. And that's one of the reasons why we chose barometric. Now, one drawback of barometric altimeters is that with varying temperature, you have to recalibrate the altimeter. So if you launched on Monday and you launched on Tuesday, there's a big variation in temperature, and you have to recalibrate because, as we know, with higher temperature, we have higher air pressure, and lower temperature, lower air pressure. Especially in Michigan. So, yeah, Michigan, we change every 5 seconds. So that's why we chose the barometric altimeter.
So this is the altimeter that we're using. It's the MTXM 2102. It has a piezoresistive sensor, and it works by differential pressure. So there's an atmospheric side and a vacuum side inside the sensor. It has a linear voltage output, which relates to your altitude. So I'm going to talk about the silicone diaphragm inside it, which is a strain gauge. And also, the sensitivity is ratiometric to the voltage supply. So this is the piezoresistive sensor. It's a silicone diaphragm connected to a pressure side and a vacuum side, as I said. And the change in the shape changes the resistivity. You can see on the right side that with the different tension on the strain gauge, it will change resistivity of the piezoresistive sensor. And that change in the shape is going to change the voltage. And when you have different pressure on the sensor, it's going to change the shape, thus the voltage. So this is the one of the pictures I think the football team showed you guys. There's a change in the shape and change in the voltage output. So increasing pressure on the atmospheric side relative to the vacuum side is going to change the output voltage and vice versa. All right, here's the differential output. This shows you a voltage supply of 10 volts. The good thing about this altimeter is it's ratiometric, so you can scale it down. I showed 3.3 volts corresponding to 13.2 millivolt span. So the only drawback of that is you lose a little bit of sensitivity per change in pressure. So you take the difference of the voltage side, the atmospheric side, and that corresponds. The atmospheric side and the vacuum side corresponds to the altitude.
Now, to interface our altimeter with the MSP430, we will be using the analog to digital conversion unit that is featured on the MSP430. And the overall outline is to take the analog voltage readings from the altimeter and store them on the microcontroller, and then compare them to a preset level. And then once MSP430 sees a match between what it stores and the predetermined level, it will toggle an output pin and eject the main parachute. But first we have to determine what the average output voltage for the altitude that we want to eject it at first. First thing you gotta do is you gotta set up the ADC10 registers, very similar to what we did in the labs. There are two main ones that you set up, ADC10, CPL0, and which is for interrupt service routines, sampling rate, and reference voltage settings, among others. And then the ADC10 CTL1, which enables analog input pins and capture and compare methods. And so once you have it activated, once the ADC is activated, your conversion results will be stored in ADC10 mem, as you very well may know. And we plan on using an if statement and a while loop for the actual comparing of data. So we compare the ADC10 mem variable to the predetermined voltage that we will decide later, and then once it gets there, it will toggle the ejection charge and deploy the parachute.
Okay, so last time we did our presentation, kind of our last presentation, that wasn't so technical, and we got some feedback that we didn't give really enough information about our actual circuit. It's more about the rocket. So just kind of give a bigger view. So we started with the altimeter and just kind of seeing how we're going to apply it. So this is just kind of like a general block diagram layout of how we're going to have our altimeter on our circuit, which will be then sitting on top of our launch pad. So next slide. So you guys have all been 480 Live and seen us working on the rocket. Basically, this is the electronics bank that we'll have inside of it and how we're going to have it set up. So we decided to actually use a 9-volt battery to have a more reliable voltage source. So we're going to have that going to the voltage regulator circuit, which will drop it down to 3.3 volts constant voltage, and then that'll go to our that'll basically go to our launch pad, which will then control our booster pack, which will have the altimeter and all of our other components on it. So as you can see here, our eBay will be inside, in between two of the tubes of the rocket where they connect. It'll have the main parachute on one side and the drogue parachute on the other. I'll give you an example of that in a second. But if you can see here, the altimeter right here in the hole for to read the pressure, and then inside this tube, it's gonna be in here, but if it's in there and it's enclosed and it's kinda airtight, then it won't be able to read pressure accurately. So we're gonna have a relatively big size hole inside so we can read, accurate outside pressure and whatnot when it's, to give it good accuracy. And then you can see here how we have the wires going to each side. I can't really see that one, but this one is the ejection charge, and we're going to be packing basically black powder, like kind of like a tablet. It's like an Alka-Seltzer size like tablet of black powder. And once we have these readings, we'll basically once it senses a certain height, it'll send a current basically and ignite the charge, blow the parachute. So that's kind of the general idea of how it's set up when you set up a rocket. And then, so like I said, the eBay will kind of be right in between here. I mean, it's a scale, but have the main parachute and the drogue parachute on one side, and then it'll be connected through like you guys saw before. So, if you got any questions? Kelly.
Will the hole inside of the rocket do anything with you guys trying to get that straight shot up?
No, so we have the thrust going up, and then we obviously have the gravity, but there's gonna be drag too. But how the nose cone is set up, I wondered about that too, and I looked it up. It's like how does the whole the whole depending on the size will affect, it'll pull one way or anything. But with the draft and the nose cone, it basically forms kind of a draft kind of blanket around the rocket, so it can be up to they said about a dime size, and you should be fine. Anybody else?
So, how do you guarantee that the rocket won't deploy the parachute during handling?
During handling?
Right.
Well, for altimeter purposes, first off, it'll be off. The circuit will be off. But if it's on, say, you just have it carrying out the battery in there. For the altimeter, it has to be at a certain altitude, so that won't set it off. But now, if you can make an argument for the accelerometer, and the accelerometer has your three axes, your X, Y, and Z, and you're going to be moving it around, say the rocket and the circuit, and that'll change the axis. And the accelerometer has a 0G bias. Basically, you have your different axes, and they compare to voltage. Like your acceleration compared to the axes and voltages is like your voltage over your sensitivity of the accelerometer, which is measured in volts per or millivolts per Gs. So either way, when it's sitting on ground, it's always going to be reading gravity, which is basically it reads as 1 G in the accelerometer. So the only way we're going to have it shoot off in how we have our code set up is when any of the axes read 0 Gs, and the only way for any of them to ever read 0 Gs or get below, get below 0, like how it's set up is, if it's above a 1.56 or 1.65 volt output, our accelerometer, if it's reading that, that's positive acceleration. Otherwise, it's just going to be sitting at 1.65 volts because it's just gravity. That's as low as it'll get. But it'll only go below that 1.65 volts negative acceleration, basically, if it's in free fall. And that's the only way it's going to reach that. So that's kind of that's at least what we're hoping for.
So you look at like that accelerometer and then the parametric change.
Yep.
Pressure change, and then you'll deploy once those are all there.
Yeah, so our plan is to use the accelerometer for the first parachute, basically. So we're going to go up and launch the rocket, which won't go straight up. They usually, they twist a little bit sometimes, depending. But either way, once they usually curve over, and then once it gets into free fall, once it starts falling, by the time it gets all the way up, the booster pack, the motor won't be firing. It'll just kind of go up, sit, and then get into free fall. And once it falls, I think about it like maybe 100 feet, then it'll read about 0 Gs. Once it hits free fall, and then it'll deploy the drogue. And then when we set it to about like 300 feet, we'll have the altimeter. We'll set that into another loop. Once that accelerometer reads that 0 Gs, then it'll go into the loop for the altimeter to read about 300 feet or whatever pressure that reads, which relates to the voltage, and then it'll deploy that main, because we don't want it reading that 300 feet, the altimeter reading that 300 feet on the way up and just blowing the
So your altimeter is directly related, or your predetermined voltage in your code is directly related to your altimeter. How are you guys gonna find that predetermined voltage?
for, just, equations.
Just set it off.
Just to set it off?
Yeah.
The equations that we use on the data sheet, basically, that they have, so they,
So you're kind of estimating
Yeah, we're
what the
kinda-
voltage will.
yeah, we're just gonna pick a safe area, like, so say like, you know, just to be safe, we're gonna pick from like 300 to 500 feet, within that range.
Okay.
So like, so it's, yeah, it's just, yeah, it's the ratio, that they can basically give in data sheets, so it's just like. And we're gonna obviously test it in lab to make sure it's accurate, which we have done already. We were gonna have a video, showing it, but it's kinda hard, cause we can only move it so far connected to the, power supply. Anybody else?
So how are you going to recalibrate for temperature? Are you going to have a temperature sensor too?
No, for the temperature, to recalibrate for temperature, they also have, ratios in the data sheet. So, say if it's really cold outside, it's not super sensitive, but if it's really cold outside, like it is right now, compared to like it was 67 degrees on Monday, then you'll have to, there's a ratio in the data sheet, which we haven't actually, I've seen and looked at the ratios, but you just basically adjust the output voltage to one of the reads of where it sits, for the pressure in relation.
Any other questions? Good, thank you.
Thank you.
Thank you.